Hi, this is your host Swapnil Bharti and we are here at Open Infrastructure Summit in Denver, Colorado. And today, once again, we have our regular Tim Bell from CERN. So first of all, it's great to see you again. Because I think you are moving into the maintenance and upgrade phase now. So
That's right.
Yeah, so tell us a bit about what is going on in there.
So CERN has periods of time while we run the accelerator, and then we have shutdowns during which time we can upgrade both the accelerator but also the experiments themselves. So we're currently just starting what's called long shutdown 2, and this will be about 18 months when we will upgrade the intensity of the collisions for the accelerator and then restart again in 2021. So it's a time of change. It's also a good opportunity at that point to be looking at reworking some of the IT infrastructure. So in the past, we've used these windows when the data isn't coming in from the accelerator to make changes in how we run things.
Right. So what are the major upgrades that are scheduled in this cycle?
So from the computing side, the thing we're really looking at is to move from a mode of running our workloads inside virtual machines to a mode where we're going containerized with Kubernetes. This will allow us to modernize the infrastructure and also reduce the overheads that some virtual machines bring to compute workloads. It's of the order of 3%, but it's worth saving.
So why did you choose to go with Kubernetes? Is it because it's buzzword these days, or it's really solving some problem for you as well?
So Kubernetes allows us to be looking at doing things like rolling out upgrades in a continuous fashion. And the system that we use for scheduling the end user workloads, HT Condor, supports the use of Kubernetes as a backend in the same way it supports virtual machines. So for us, it's a transition that we can do without disturbing the user community, but allows us to take advantage of the shutdown to upgrade the infrastructure and be a more flexible infrastructure for the future.
And I'm expecting that you are running upstream version of Kubernetes, or you are using some distribution?
So we're using the upstream Kubernetes. I forget the very latest one, but it's 1.13 or 1.4.
1.4, right? Yeah.
Yes. So as usual, we look to use the open source versions of software, so equally we can contribute back to the communities and see those changes in a short term back at CERN.
Right. So you're involved with OpenStack. You are involved with Kubernetes, and you are doing a lot of work in other open source communities as well. So where do you bring these resources from within CERN? We have spoken about it last time also, that a lot of volunteers come, a lot of people come from other agencies as well, and people from companies also come and they work with you.
That's right.
So when you said you also contribute back, so let's take an example of Kubernetes. How do you engage with the community?
So to take a Kubernetes example, we recently had someone join the team. They just finished their PhD and they were working for 1 year at CERN, and their work involved integrating the Ceph file system into Kubernetes using the new CSI interfaces. So this allows us to provide an open source file system like CephFS, work with the Kubernetes community and provide that glue so that for the end users, they don't need to know all about the underlying infrastructure, they just consume Kubernetes as a service. And then they just choose what they would like as part of that. So it means working with the Ceph community, working with the Kubernetes community, and working with the OpenStack community.
And I think there are more communities you work with. These are not the only ones.
Right.
Yeah,
so the overall approach is that we use open source as a vehicle for us to enhance our IT environment, but also as a way for CERN as a publicly funded organization to be giving back to the rest of the world.
Right.
Since the World Wide Web came along, we put the web into the public domain. It's very much part of the organization's culture. Mm-hmm. And equally, working with open communities is something that the people find very rewarding, because it allows them not only to be doing something that has a visible record, but also when they come to the end of their time at CERN, they've got the opportunities to go and potentially work with other companies that are working in these areas. So they therefore have a very good trampoline into future employment too.
Right. Before we talk more about this upgrade, I just want to give our viewers, an idea the scale at which CERN works, when it comes to data or how many cores you're running. So can you just quickly tell us about that?
So the CERN OpenStack cloud is about 300,000 cores.
300,000 cores?
Yes.
Okay.
So that's about 9,000 hypervisors. In terms of total data sets, we recently passed the 300 petabyte data volume. So that means that we have all the data from experiments back to the 1970s that we keep archived at CERN, and we actively use tape as a medium for archiving this data for longer term analysis after that. And then there is a cache of hundreds of petabytes of disk store between the tape and the actual working compute nodes. So it's a big environment,
right.
But equally, when we look at other sciences, we see they are following very similar patterns, and the large web companies form much, much larger environments. So it means we're no longer at the leading edge.
Right. Yeah. So in typical, when the accelerator is running, of course, a lot of science is going on, but a lot of technology is also going on in there. So what are the things that keeps you worried, or you have done everything fail safe? So I just want to get an overview, because this is a massive project, Yes. You showed a picture at one slide, I think somebody from, it's like a gigantic, like a cathedral or bigger than that.
So a standard experiment will be of the height of Westminster Cathedral, weigh 7,000 tons, and take 100 megapixel photos 40 million times a second. So this produces about 1 petabyte a second of data to be processed.
Okay.
Behind that, you've then got the massive engineering effort to produce an accelerator that is using cryogenics, liquid helium, cooled down to minus 271 degrees centigrade. There are areas in engineering, in physics, in computing, where we're really pushing the frontiers of science. So that's where it's good to be working with other people to solve those difficult problems, be it companies or other labs that are trying to do the same thing.
What keeps you worried when they're running their science projects?
I think the systems itself are actually surprisingly resilient.
But you have made it in that way, right?
Right.
They're not magically.
No, and one of the things that's good about high energy physics computing is its high throughput. So each collision is independent. The important thing during data taking is to get the data from the experiment to tape. After it's on tape, then at that point we can reprocess it and have more failure scenarios.
Okay.
And then we collaborate with about 170 labs around the world who help us with compute resources to analyze this. So the system itself is quite distributed and therefore quite redundant once we get the data from the accelerator. There is only one accelerator.
There's only one, yeah. Now let's go back to the point of upgrade. After this upgrade, what new capabilities will the accelerator gain?
So the primary change for the accelerator will be to increase the intensity of the collisions. So what that means is that collisions at the moment involve bunches of protons passing through each other. Some of them collide, some of them don't, and they go round the ring again and then they collide again. So in the upgrade, then we're facing a situation where there'll be far more collisions per second, including multiple collisions happening simultaneously. And these require significant more computing power to process. So that makes it for a really difficult computing problem to take multiple collisions, separate out the particles that are produced. This will lead to probably an order of magnitude increase in terms of our need to process. Can we optimize the programs? Can we get the computing capacity available? Is something we're looking at over the next 2 years.
Right. And how does the move from VMs to containers and Kubernetes going to impact the efficiency or performance overall?
So in the transition from VMs to Kubernetes in itself, there won't be a significant change for the program execution. Where it will help us is in the administration of those environments. So being in a situation where we can roll out, for example, a security patch as a rolling upgrade rather than a campaign where the administrators need to write scripts will be very attractive. So using Kubernetes orchestration to deploy change will be a very flexible way of doing it. The other aspect is that users, the physicists, are increasingly using Kubernetes as a way to package their programs. So for them to have containers that allow them to save the way they've done analysis and then rerun potentially in a few years' time the same analysis to validate the results on new data is very attractive for the end users. So it's more of an operational benefit and a functionality than for a performance.
You also keep an eye on the next shiny object in the tech world. So what are the technologies that are being developed or in a very nascent stage that you are interested in?
We're looking a lot at newer accelerators, GPUs, in order to try and work out how can we use some of these technologies that are widely used for internet recognition, deep learning, and apply those to a research area. There are some applications which are already obvious around the detectors. To have something that's able to detect interesting events is a very useful application. Equally, how we apply GPUs in an environment is one of those challenges to find the right cost balance. Lots of GPUs get to be expensive, so you need to make sure you can use them efficiently and use them throughout the whole program, and that means reworking the application code as well. But it has the potential to then bring online significant improvements in performance for physics workloads if we can find how to use industry standard GPUs for research.
So are you working with the GPU players on exploring this?
So CERN works with industry through the CERN Open Lab program.
Okay.
We take difficult problems, we work on them together. So a recent company that's joined is E4, which is a manufacturer in Italy. And we're working with them and NVIDIA in order to look at how do we apply these technologies. Micron has also recently joined this team, and we're looking there at FPGAs and accelerators. Just how we can use these technologies at the moment is a really interesting problem.
Right.
Many of them are quite small footprints, but we actually have quite big code, and finding how to squeeze that in is going to be an interesting challenge as part of the Micron work.
And that's what CERN is good at, right? Solving complex problems.
The idea is that we solve those complex problems such that when industry needs the solutions, we have already validated them in a pretty tough computing environment.
Right. You also mentioned deep learning. Last time also we talked and you said, when you look at it, you don't even know what to look at, so you cannot have a machine learning model there. So what role does deep learning play in accelerator?
So I think it's very difficult to ask a model to identify the next Nobel Prize.
Exactly.
But what you can do is to use it to identify anomalies. So basically you can understand what is the known physics, and then with that be able to extract out things that are not well known. But this is the big area of research, is how do we find ways to use these technologies and these frameworks to apply them to physics problems. And yes, it's not a known problem yet.
Right.
In fact, we even had a workshop on quantum computing last year, where we've been looking at how we can potentially apply quantum technologies to physics. That, however, is probably beyond the next run before we get to useful applications.
Right. So what are your thoughts on quantum? I mean, we have been hearing about quantum computing a lot, especially if somebody has seen Endgame, they know quantum realm a lot. But quantum computers, I talk to people at D-Waves, they do a lot of work. They solve different problems. We will never see a quantum computer in our phone, probably never. So can you talk about how different are they from HPC or supercomputer versus quantum computer?
Quantum computing actually as an application was quite an interesting one for us, because one of the things that many of these systems require is to be cooled significantly.
Yes.
And so this is something which CERN is very used to. In fact, often some of the quantum computers need to be cooled down further than the accelerator. So at the moment, it's very much a matter of understanding how to apply some of these technologies to the CERN computing problems. And I don't think we'll solve all of the problems this way. It'll be more a question, maybe we can identify some applications where this is a very useful application.
Right.
But yes, having seen some of the models, I'm not expecting a smartphone to be quantum-based in the near future.
Right.
But there again, if we look back 20 years, people wouldn't have thought of a way to have a network of knowledge across the world where you could trivially search for anything you needed.
Anything else you would like to talk about? Because we touched upon the upgrade, we touched upon the future technology that you're interested in, we talked about the amount of data you generate. Anything else you would like to talk about? Or do you think we have...
I think the other aspect of the summit here has been interesting, has been the additional projects. So Zool, Airship, Kata Containers, Starling X. So gradually, as we start to look at bringing in some additional projects, along with additional people working on it, it's been very interesting to actually look at things like edge computing.
Yes.
We're doing at CERN a lot of Internet of Things. The accelerator has so many sensors.
And how many are there?
I am not sure on the exact numbers, but we're certainly talking thousands.
Yeah.
And I think with that, then we're starting to see opportunities for multiple different and independent industries to start working together. The combination of all of the work that's going on in NFV has direct applications to some of the things at CERN. I was talking earlier with some television production companies who are using identical storage technologies to the ones we're using and are facing similar problems. So from that point of view, I think bringing in some additional areas, working with other foundations like Ceph and Kubernetes and the Linux Foundation, really gets the best out of open source as a collaboration vehicle.
So we talked about science, we talked about, last time we also talked about science fiction, but one thing we never discussed was that, what are your hobbies? What do you do in your free time? I hope you're not writing some science fiction because you have so much access to tech and science.
I think one of the great things that I've found since moving to Geneva has been that in an area like Geneva, you've got the mountains all around. So the nearest skiing resort is half an hour away, and then during the summer you can go hiking in the Jura and Alps. So it's a really nice environment to be bringing up a family in, and therefore with that get to see some of nature as well as looking at the computer screen during the day.
It's really great to talk to you once again, and I'm looking forward to talk to you again to get more updates. And by that time, maybe we'll find something else and something better, something more powerful.
Hope so.
Yeah.
That'd be
Thank
really
you.
good. Okay, great, thanks.